Hello. So I'm going to talk about angelic checking within Static Driver Verifier, how to find high precision defects without a lot of modeling cost. So my name is Shubhendu Lahiri. I work at Microsoft Research. This is joint work with several of my colleagues, Akash Lal, Vladimir Levin, Rahul Kumar, Nate Desinger, Jakob Lichtenberg, and Chetan Bansal at Microsoft, and our former interns, Sridhar and Alexander. So in this talk, I'll touch upon some well-known limitations of software model checkers. SLAM, Corral are two of those, but there are many others in recent years. And how do we address these limitations using a technique called angelic verification? And then we mostly describe our experience of prototyping and deploying these angelic checks in a tool called Static Driver Verifier. This is an experience that almost spans 4 years since we wrote the technical paper on the angelic verification. So some of you know the Static Driver Verifier is a tool that is used by Windows driver developers to find bugs in their drivers. The project SLAM, which was the underlying model checker, pioneered sort of the use of model checking for finding defects in real-world software. So this is the article back in 2010 on how SLAM helped with the Static Driver Verifier tool. And here is the tool. It's still maintained. There is a product group that maintains it, and it is used in the driver ecosystem fairly heavily. So after SLAM, there's been progression in SDV. One of the big changes came when the tool Corral, which is a property-directed bounded model checker, was used to replace the SLAM model checker. So Corral, as opposed to SLAM, SLAM was driven more by proofs. Corral was driven primarily to find bugs because of the bounded nature, and it leveraged SMT solvers as they became more and more mature and faster. So it led to a lot more defects, and a lot more problems could be solved using Corral. So as the tool matured, the underlying model checkers also matured. So the natural question is, why can't we use SDV with Corral to find all software bugs, let's say in drivers? Like, do they find all the bugs? The answer is no. And why is that the case? So I think the more appropriate question would be, why cannot SDV and Corral find all software bugs with high precision? Because you can always flag all assertions as violations, and then you have all the bugs. So that is the central question. Why do software model checkers miss bugs? This is the story of SDV, but I think it's the story of any mature software verifier that is based on model checking. So SDV requires a lot of upfront investment. So for the domain, it works the best, drivers, specific classes of drivers, it needs driver expertise to write very specialized drivers or harnesses of how the driver APIs are called. So that's one part of the story. The other part of the story is you also need to write models of how the driver interacts with the kernel, because SDV was primarily used towards finding these interaction bugs between drivers and the OS. And these models and harnesses have to be kept up with the changes in the OS, and it requires a lot of investment. It took a decade of investment to where SDV is today to get these models. It's something that doesn't get as much attention in the software verification community, the need to model and create harnesses, but this is the story. So as a result of this upfront investment, this verification methodology is very difficult to scale towards, um, extend towards new classes of drivers. If a new class of driver comes along, adapting SDV to the new class is non-trivial because it needs these investments. Secondly, memory safety properties. These are properties about the driver itself, the memory corruption, and that's very hard, as I will, it's again because of modeling, but there are other issues that I'll touch upon. So as a result, SDV cannot find a lot of bugs that happen in practice, either related to memory safety, security critical properties, or in drivers that are not in the not captured by SDV, SDV's models and harnesses. So if you think more about it, there are two essential problems. One is that of precision. So if you don't do modeling, essentially you're left with analyzing open programs, and that leads to an under-constrained environment of where the code executes. The second is that of scalability. As programs grow larger, since we are using a path-sensitive analysis, it can the analysis can quickly suffer from the exponential blow-up of paths, even in spite of all the abstraction, refinement, progress that has been done in model checking. So in addition, as you have more and more assertions, for example, memory safety rules, this adds to the scalability issues. Finally, if you have a method that is deeply nested in the module, finding a trace all the way from main is very hard. So all these issues contribute to the scalability issues to find bugs. So regarding the open program problem, so most model checkers like Corral work on closed programs. What that means is they have a main and they do not call into APIs that do not have a body definition. So what happens when we analyze open programs? So what happens is that these model checkers, since they are very precise, but they make the worst case assumption about the environment. So that's the reason you need modeling. So let's look at an example here. So here is an example of a use after free check on some program. And it consists of 3 lines, and these 3 lines could be spread across procedures. They need not be next to each other. Let's just say we have a trace that consists of these 3 lines. So the specification of free is on the side, which says X should not be freed already, so it should not be double free. And then it sets the freed bit of X to true using a map. And this is written in a low-level language called Boogie, but you can imagine having these kind of maps to add go state, the type state. And before every usage, like a dereference of Y, you add an assertion that Y is not freed. So if you give this program to the model checker without any context, it is going to happily find counterexamples that show that all 3 accesses are violations of the use after free rule. But if you squint a little bit, the first 2 looked a little bit pessimistic because you don't know whether X was freed or not. You don't have much evidence whether X was freed. Similarly, you don't have evidence whether X and Y were aliased or Y was freed before. So without looking at the context, it seems it's overly pessimistic in thinking of these as defects. And this kind of reasoning, demonic reasoning, leads to lots of false alarms if you do not have a closed program. So angelic verification is one idea, simple idea to suppress defects with specification inference. In this case, it boils down to precondition inference, but you can have other cases where you have to deal with return values from external APIs. So in this case, instead of asking, can you violate these assertions, you can ask, well, is there an acceptable specification over the environment that can hide the alarms? And here the environment is the value, the type state of X, the aliasing of X and Y, and so on. So in this case, you can come up with a specification that says X and Y were not freed and X is not aliased with Y. With that specification, you can remove the violation of the first two assertions, but you still retain the third one, which most likely looks like a bug according to the specification that we've written. So this helps prioritize high quality defects. So the AV tool flow, the way it works is it takes an open program, a module, it creates a closed program, but by what we call Angelic harness. And then it uses repeatedly a path sensitive verifier like Corral, and then it infers specifications, a fee, and if the specification is permissive, then it would block the assertion with the specification and keep repeating until we either find a bunch of warnings or the entire program is verified modulo the preconditions or specifications. So the permissiveness ensures that the specification is not too strict, like it does not become false or it does not create dead code. So there are a lot of parameters in AV about what the vocabulary of specification is. It is parameterized. You can say, I would like to remove non-aliasing constraints because I know aliasing is pretty common in my modules. Or you can also talk about whether we include indirect flows in the specifications, whether you use control flows to block specification, to block the errors, or do you just treat the control flows as non-deterministic control flows for the purpose of blocking? And then there are various notions of permissiveness. So this was the tool that we prototyped a few years back. And interestingly, AV also helps not only with the precision problem, but also scalability in the following sense. So if you have methods that are deeply nested inside a large module, it may be very hard to reach that method starting from the entry point main. But with AV, you could start your analysis at any method. And if your bug is localized to a few procedures starting at that method, then you can find it with a high evidence without having to start all the way from the main, because AV takes care of hiding false alarms that result from an unconstrained environment. Okay, so this paper would describe how AV was used to help SDV, the Static Driver Verifier, by adding these angelic checks. So what are angelic checks? So these are checks that where we reveal defects only when they cannot be blocked by simple specifications in our vocabulary, right? Simple meaning they are in our vocabulary and they are permissive. So in a way, it is prioritizing precision at the cost of recall. It might hide a few real defects because the specification might be too strong or incorrect. But when it shows a defect, there is usually high evidence that in the trace itself that shows the violation. So in this paper, we demonstrate how we create a whole bunch of memory safety rules, temporal memory safety rules, including null check, use after free, double fetch, and more traditional SDV rules that check for interrupt request levels of drivers, but that can be applied to any driver, not just limited to the drivers for which SDV has harnesses and stubs. So the paper has more description. I'm just going to touch upon these rules. So null check, we not much to it. It checks that null valued pointers are not dereferenced. Use after free, we saw an example. A freed pointer should not be used, or a freed again. The interesting aspect is double fetch rule. It's a rule that has been in focus in recent years because of the security implications. So it checks that a field in a user land pointer is read exactly once within the kernel. So what's the user land pointer? So it's a pointer that a user can control. And what happens is that if you look at this example, the method foo, which you can think of as a kernel entry point, has a pointer argument x, and it has a field called length. And you can see length is read in two places. First, to get the len itself, and then as an argument to the RTL copy memory. So there are security implications where a user in the window between the first read and the second read can alter the value of length, and that might result in underflows, overflows when buffers are being copied inside the kernel, and that this can lead to many well-known information disclosure or security critical exploits. So that's a very important rule for kernels, both in Windows and in Linux and other operating systems. So of these three, use after free and double fetch are known to be security critical. And all these memory safety rules, they add several more assertions to the program than compared to rules that check for certain API calls. Like if you just want to check whether a lock is followed by unlock, say it requires tracking only a few API calls. However, tracking memory safety requires much denser assertions in the program. So typically hundreds to thousands of assertions on any real world program is pretty common. So this makes it much more challenging to verify all these checks. So in addition to memory safety rules that were new to SDV, we also added a more traditional rule called IRQL checking. So what the rule does is it ensures that when certain OS APIs are invoked, they are invoked at the appropriate interrupt request level. So this avoids what people call kernel panic when you call an API at an unexpected interrupt, and it can either mask higher priority tasks or enable lower priority tasks. So these are reasonably well specified in MSDN for developers. So you could write the checks independent of the driver as a set of rules, and we spent a person month to write these around 500 rules that capture the appropriate request level for an API and how an API might change the interrupt request level. So on this example on the right, the first call EX acquire fast mutex, it has a requirement of the IRQL being less than equal to 1, and it also alters the interrupt request level variable to 1 after this method is called. Similarly, there are IRQL levels for other APIs. We did not, unlike STV's prior rules, let's call them non-angelic rules, we did not require these rules to be specific to certain class of drivers. So you could take any module that calls an API that has a specification, and you can check it. So in addition to the previous defects, we also found it was useful to look at inconsistency traces. So in this example, there are two branches. The first branch tries to call EX acquire fast mutex. the second branch, K, tried to acquire spin lock at DPC level. So you can imagine that an AV like tool would infer for the first branch, the URQL has to be less than equal to 1. For the second branch, URQL has to be less than equal to 2. Each by themselves is perfectly reasonable, but when they combine, they lead to a inconsistent specification false. And we say this is an inconsistent trace, a pair of traces, because the evidence is actually two traces, not just one trace. So this was quite useful in the context of URQL rules. So the instrumentation, so in the implementation, we also built a new language to specify these AV rules, properties, and instrumenter that takes a property, an AV property, let's call Angelic Check, and a boogie program, and then instruments the boogie program with the property. So it can do very low level instrumentation, tracking memory accesses and things like that. There's an alias analysis component that does an aggressive pruning of assertions that can be verified with just path insensitive analysis. And we also exercise the knobs present using AV. The vocabulary was mostly consisting of type state specifications, non-aliasing specifications. And for URQL, we needed to add some arithmetic over the environment constants like URQL variable. And we also decided for scalability and also to find more bugs to only block the data flow. What that means is that we do not try to infer specifications that are conditional on the path taken, the path condition taken. So that lets us be more scalable and also finds more defects. So this is a balance we found empirically. Okay, so here are the results. So we looked at almost 1,000 drivers across the 4 rules. For null check, we looked at the regression suite of SDV, which is fairly comprehensive, about 200 drivers. Use after free, around 65 drivers that have some notion of free in the driver. Double fetch, we focused on one which had a known defect, and IRQL check had many drivers that had some IRQL call. And we found more than 100 bugs. For double fetch, we were able to find 10 more defects, which were variants of the known defect, which were all new defects, which was very nice. Okay, so there were still false alarms that were interesting. So for null check, there were a couple of cases where to prevent the false alarm, you would need an OS model that needs to reason about linked lists in a method that talks about removing a linked list head, and another API that requires some detailed knowledge of driver stack, which requires some Go state. So we did not feel it was cost effective because the few examples that were flagged false alarm because of this. Cost effective yet, maybe the driver developers add them in the future. So those are the false alarms. For use after free, we found an interesting case. So look at the procedure foo here. So it increments the reference count, calls bar, which decrements the reference count. And if the reference count goes to 0, then calls free. And then there is a usage in foo itself. So AV thinks this is a warning because it actually sees evidence of free and dereference in the same procedure starting from foo. But there is an implicit precondition that foo is always invoked with a reference count greater than 0, which means that from the foo's call site of bar, the free is never exercised. So this is an implicit precondition that we don't know because we start analysis from every method, as opposed to just the entry point of the driver. So this is there's room for research in how do you find better specifications here to know that you need to track the reference count condition as part of this specification. So, and for IRQL check, we had one case where there was a very rare aliasing with a global variable that the alias analysis did not rule out. So again, it was just one example of these defects. So this was the prototyping, and once we prototype, we've been shipping these rules within the SDV starting in 2016. So these are the rules I mentioned. Double fetch is in private preview and would be available in the next WDK release. The null check rule, which is most exercised now and has found lots of defects, is documented on MSDN. You can take a look. And use after free and double fetch are security critical, so they're important. And they're enabled for any driver. And as in the course of internal deployment, we also found several security critical bugs, at least one of which led to OS security update. So in summary, we touched upon the limitations of precise software model checkers related to precision and scalability, how we attempted to address those limitations with Angelic Verification, our experience prototyping these checks, and the results. And in future directions, I mean, there are new rules being developed by product team in conjunction with us. We still have a long way to go about scalability. AV is not scalable, it's not compositional, it reanalyzes methods that have already been analyzed. And there are false negatives that are suppressed by AV that we would like to address as well. So yeah, so here are the resources for AV. There's a project page and there is a tool page where you can play with the AV tool. It only works at the boogie level, so the front end that goes from C to boogie can be any of the front ends. We use one specific one in Microsoft that is unfortunately not open source, but we have some experience with SMAC and AV that we worked on a few years back. Okay, so that's the talk. Thank you.